Good day, stat students. So today we're going to start chapter 8. Specifically, we're going to go over sections 8.1 through 8.3. So we'll start with a random variable. So this is a variable whose value that comes from an experiment or random sample. So before we just talked about variables in general, okay? And here it's a random variable because it comes from an experiment that is randomized. Okay, remember we randomize treatments and stuff, okay? And then we have random samples, okay? And so these things would produce a random variable. Now, this definition suggests that random variables are only quantitative. Why? Because it says variable whose value, okay? So since the variable is producing a value, um, random variables really are only quantitative in nature. So let's think about the quantitative variables. We have discrete and we have continuous. So we have discrete random variables and we have continuous random variables. And what we have to realize, this is important, okay? This is important. There's different rules for the discrete random variables versus the continuous random variables, and we have to keep them straight. Today, we're going to go over the discrete random variable stuff. So first, we look at the rules that apply to all random variables. That's what we're doing with these slides today. We're going to go over the rules that apply to all discrete random variables. In other sections, okay, not these slides here, but in other future sections, we are going to look at specific discrete random variables, okay? But today, we're going to look at the rules that apply to all discrete random variables. All right, so we have some notation for the probability. So we have, big X. Big X, we would define somehow, okay? We would define that variable. Here, we would say let X maybe be the number of cars a family owns, okay? And maybe we did a random sample to produce this, okay? And then we would say it is equal to little x. What is little x? Little x is the value that big X can assume, okay? And so notice this difference between this and the book, okay? The book uses k and then eventually changes over to x, and they are so close in definition that there's no reason to do it. And so let's just say that I'm going to stick with little x because eventually the book changes over to that, okay? And so let's not confuse things. We're just going to use this notation throughout this section or these sections, okay? I think you'll find it easier. So we have a probability distribution function. Acronym is PDF, okay? You might also hear this a lot of people call this a probability distribution and drop the word function. So if people call it probability distribution, they're talking about a probability distribution function, all right? And it's a table or formula that assigns possible values of X and along with its corresponding probabilities. So let's say that big X is equal to the number of natural siblings a person has, and so we're not talking about any like half siblings, okay? We're talking, either you can have 0 or 1 or 2 or 3 siblings, okay? Natural siblings, okay? And so let's say I went around the room in class and I was able to create this table. So notice that I said that a probability distribution function can be a table or a formula. Here I have a table, and here are the different values that X can assume. So 0, 1, 2, and 3. No one had in the classroom 4 siblings, okay? And here are the corresponding probabilities for each one of these. And so what this is telling us is that 0 shows up 10% of the time, 1 shows up 30% of the time, and so on and so forth. Okay, so we can have a table to organize the stuff. And this table will be comprehensive. And what I mean by that is that it's going to give all the values of X, okay? So it won't shortchange in any way. Probabilities are going to be valid, so that's kind of obvious. The sum of the probabilities will add up to 1 since we have all the X's there. And this should be thought of as this is for the entire population. It's usually not thought of as a sample. This is thought of that it's applying to the entire population. All right. So let's develop a PDF for a discrete random variable. Okay, so we have to define the discrete random variable first. So we have let big X equal the sum of a roll of two six-sided dice. So, like Monopoly. Okay, you play Monopoly, you have two six-sided dice. Okay, you roll. That's a um, that's going to be something that happens randomly. Okay, and so we have the sum of a roll of two six-sided dice. Okay. By the way, there's a game, there's a casino game in uh, in Vegas or well, you can play it here now for the most part. Uh, but there's a game called Craps that the whole payout system is based upon this probability distribution function. Okay, so let's think about this. What's the smallest sum that you could get from rolling two six-sided dice? Well, uh, lowest number that you can get is 2. Okay, and the combination that we can get there is just having a 1 and a 1, right? Okay, how about a 3? Now, be careful with this, and I did this on purpose. I hope, well, if you are colorblind, notice what I did here is that I made the 1 here red and the 2 blue. And notice here I made the 2 red and the 1 blue. So notice these are two different combinations. So what you got to think of is that you have two separate dice. One is red, one is blue. Okay, and as long as you can have a unique combination based upon those dice, you have a different combination then with regards to this. Okay, and so you can have the red one a 1, blue 1 a 2, and then a different combination would be a 2 for the red, 1 for the blue. Those are different combinations. Okay. 4, those are the different combinations there. 1, 3, 2, 2, 3, 1. Okay. I kind of filled it up to 7. So notice what happened here is that it kept on going up and up and up, meaning the number of combinations increased by 1 as we kept on going up. Let's see if it continues here as we move up to 8. So 8, notice here, it actually went down. We had one less combination. And when we go to 9 and 10, 11, and 12, it keeps on going down, okay? And so this is kind of interesting. We have to investigate eventually, not today, but I'm going to bring something up, is that this turned out to be what? A nice bell-shaped curve, okay? With regards to this probability distribution. We have to figure out why, but that's down the line, okay? But hopefully it kind of piques your curiosity a little bit. Okay, now we're going to assign probabilities. Since there were two six-sided dice, that tells us that there's 36 combinations here. You have 6 on one die, 6 on another. You multiply those two, you got 36 different combinations. Okay, and so that's telling us then that the probability of rolling a 2, well, there's only one combination here out of 36 that would produce that. There are 2 here out of 36 that would produce a 3. There's 3 here, so on and so forth, okay? So here are all the corresponding probabilities, and if you added all those up, you would get 1, okay? Here would be a probability distribution. Honestly, we don't need the combinations. We just use the combinations here to help us figure out the probabilities. So as long as we had this column here, okay, we got ourselves a valid probability distribution. Here are the values of x and their corresponding probabilities. Okay. All right. So what can we do with this table then? Well, we could say, well, what is the probability that x is equal to 4? So what's the probability that we roll a 4 for the sum, right? And so we take a look here. Well, it would be simply what? 3 out of 36. Well, we can get a little bit more sophisticated than that. We could ask, well, what is the probability that x is less than 4? So we don't want to include 4. And so what are all the values that are less than 4? We have 2 and 3. And so this is, I would say this is shorthand. Okay, this is a shorthand. And shorthand for what? We could say the probability that x is equal to 2, all right, plus the probability that x is equal to 3, okay? That's just a shorthand way of showing that, okay? All right, so let's get past that. So we go to our table, got the probability that x equal to 2, that'd be 1 out of 36. For 3, 2 out of 36, and we simply add that up, so it would be 3 out of 36, okay? All right, notice I put an equal to sign here, less than or equal to 4. Now we're going to include 4. That makes a big difference in the discrete world. In the discrete world, that's absolutely important to note, okay? That's important to note that once you throw the equal to sign there, oh, okay, we got to include now 4, right? So I believe if you take a look at those values, we would get 6 out of 36, and I could care less that we reduce the fraction or not. You can just leave it like that, 6 out of 36, just fine, okay? How about greater than? Here I put greater than or equal to. So let's see, we got the equal to sign. We got to include the 9. So now we got 4 out of 36, 3 out of 36, 2 out of 36, 1 out of 36. We got to add those up, okay? And we get 10 out of 36 now for that one. Okay? How about this one? This one, let's take our time with this one. If you know what this is, I apologize, okay? I'm going to take my time with this one because students sometimes get a little confused about this. Let's just take our time. So what I always tell students when we run into this, where we have the letter in the middle, 2 and numbers, that these are always going to be less than or equal to these signs here, okay? These signs will either be less than or equal to, okay? And what I tell students is first, just take away the signs, okay? And it helps students to visualize what's going on here. Where is x located? X is literally located between what? 3 and 8, okay? That's all we're trying to show with this, okay? All we're trying to show here, okay, is that x is sitting between 3 and 8, okay? So that means we want the numbers we know for right now we want 4, 5, 6, and 7. We know that. We want 4, 5, 6, and 7, okay? So we're not done though, okay? If we have a less than or greater than sign, then we don't include the end values or value or values. If we have a less than or equal to or greater than or equal to, then we're going to include those end values depending on where they're sitting. Okay. Here we got the probability that x is somewhere between 3 and 8. We know that. And since we have the equal to sign here, we're going to include 8. So include 8, but don't include 3, right? Because we don't have the equal to sign down there. So don't include 3, but include 8. So what does that mean? We want to include 4, 5, 6, 7, and 8. But not 3. Okay, not 3. We go to our table. Okay, let's see, 4, we got 3, and then 5, we got 4, and so on and so forth. We add those up. I believe we're going to get 23 out of 36. Okay. All right. Expected value. Expected value. Believe it or not, this is another name for the population mean. This can also be interpreted as the mean value obtained from doing an experiment an infinite amount of times. So let's say you did an experiment, okay, and you wrote down the result. Then you did the experiment again under the same conditions. You wrote down the result, and so on and so forth. You did that an infinite amount of times and averaged all the results, okay? It would give you the expected value. In other words, it would give you the population mean, okay, because you did the experiment an infinite amount of times. So you can average all those numbers and get basically mu, okay? So the notation here is E with the capital X in parentheses, and that's equal to mu, like I just said. All right, population mean. So expected value is equal to the population mean mu. For every discrete random variable, the formula for the expected value is the following. Okay, it's a summation. It's a simple formula. Here it is. It's a summation of x, all your x's, and multiply it by its corresponding probabilities. And after we multiply the x's times the p's, okay, the x's times the corresponding probabilities, we sum them. So this p right here, this little p stands for the corresponding probabilities that are associated with those little x's. Now, to show you that mu is the same as the expected value, let's go through this simple example. All right, let's say that we have a bag, and in this bag we have 10 pieces of paper, the number on each one of them. The numbers that are on pieces of paper, we have 4 1s, 3 2s, 2 3s, 1 4. So let's go ahead and calculate the population mean, okay? And we know how to do that. Since I said these are all the 10, this is the only 10 pieces of paper that are in the bag, that's our population. We can go ahead and add up those values, okay, and divide by 10, and we get 2. So we know that the mean value of these numbers right here turns out to be 2, okay? So we're going to put that off to the side for right now, okay? We know that mu is equal to 2, all right? But what we're going to do is we're going to change these raw pieces of data here, okay, and change them into a probability distribution function, okay, really a probability distribution table, okay, so I'm going to show it into a table, okay. Well, what are all the different values that x can take on? We can have 1, 2, 3, or 4, right? What are the corresponding probabilities? Well, how often does 1 show up? Well, let's see. 1 shows up 4 out of 10, right, or 0.4. How often does 2 show up? 3 out of 10. How often does 3 show up? 2 out of 10. How often does 4 show up? 1 out of 10. Okay, those probabilities will add up to 1. They do. And notice all we have to do is take the x and multiply it by its corresponding probability. So we're going to take 1 times 0.4 and we get 0.4. Then we're going to take 2 times 0.3 and we get 0.6. Then we're going to take 3, so just imagine having a multiplication sign here, okay, and multiplying across. All right, that's all we're doing. And think of this as an equal to sign right here. And this is the values that we get. And so this formula says, okay, after you do all that, you do that for all the x's, add them up, right? So let's add them up. When we add them up, we get 2, right? That shouldn't surprise us, okay? Why? Because that should match exactly what mu is. Okay, should have added up to 2. So what you have to understand is that when we went ahead and calculated a mean before, okay, and you've done this 1,000 times in your life, well, maybe not 1,000, but many times in your life, is that you took all the values of x and divided it by number of observations, right? Well, that only works. I have to stress this. This formula, right, that I put in red here, that I just wrote out, that is only for raw data, okay? To figure out the mean of the raw data, you would use that formula. However, if you have a probability distribution, okay, there you go, all right? You have a discrete random variable, okay? And that discrete random variable's data was turned into a probability distribution. You got to use that formula. But they're getting you to the same point, okay? So there's different ways of calculating a mean depending on the situation that you have. Again, there's different formulas to calculating a mean, and it just depends on the situation that you have. You can't always revert to this. This is only good for raw data. This is good for a discrete probability distribution function. And we're going to see this over and over and over again throughout the course, okay? All right, so let's figure out the standard deviation of x, meaning sigma, because we're talking about a population standard deviation, using a PDF, probability distribution function, or using a probability distribution table. All right, so since we are talking about all the x's, okay, since we're talking about all the x's, all right, that would be sigma, okay, and what we have to do is we have to take each one of our x's, subtract off mu, square each one of those, multiply by its corresponding probability, meaning the probability that x shows up, okay, how often x shows up, all right, and then take all those values and add them up. This is less complicated than what you think, okay? So, here's the table. We'll get to that note here in a little bit. Here's the table, and so notice what we got to do. Oh, I got my wrong one out. There we go. Let's take each one of the x's and subtract off mu. All right, now we know what mu is. Mu is equal to 2. So let's start with our first x. We got 1 minus 2, that's a negative 1. 2 minus 2, that's 0. 3 minus 2, 1. 4 minus 2, 2. So we just did, in this column right here, stuff that's in parentheses. Then it says take each one of those and square them. Okay, so I did that in the next column here. Okay, and so I squared them here. So I squared those values and put them over here. Then I took those values and multiplied by how often x shows up, okay, which is over here. So we took 1 times 0.4, 0.4, 0.3 times 0, 0, 0.2 times 1, 0.2, 0.1 times 2, 0.4. And the last step is that it said take all of those guys and do what with them? Add them up. So we take all those and add them up. What do we get? We get 1. Okay, we get 1 in this situation. So that means if 1 shows up 40% of the time, 2 shows up 30% of the time, 3 shows up 20% of the time, 4 shows up 10% of the time, okay? What that's telling us, if we actually figured out the standard deviation based upon the raw numbers, it would come out to 1, okay? Now, I want you to note something, okay? Don't try and use the sample standard deviation formula that I gave you earlier in the semester to see if it matches with this one. Now be careful here, okay? This is the reason why. Pay attention, okay? The population standard deviation formula is slightly different than the sample standard deviation formula for raw data, okay? I gave you the sample standard deviation formula, which most of the time, that's what most people need, okay? However, please note that for raw data, sigma is slightly different than the sample. The population standard deviation is slightly different than the sample standard deviation. Okay, and so you gotta make sure that you get that and understand that. Okay, now I don't expect you to know this formula here. Okay, but I just want you to note, especially if you are in statistics. Okay, and you plan on taking more stats courses because you might run into that later on. Okay, all right, thank you for your time.